Hi, I'm Calvin, and welcome back to my series on unsupervised machine learning. In the last video, we explored k-means clustering. Today, we're moving on to another clustering method called DBSCAN. As usual, I will have the code and materials in this video linked down in the description if you'd like to dive into the code after the video or follow along to this tutorial. So, what is DBSCAN? DBSCAN stands for Density-Based Spatial Clustering of Applications with Noise. Unlike k-means, which we covered in part 1, which requires you to set the number of clusters up front, DBSCAN groups together points that are in dense regions and marks points in sparse regions as noise or outliers. This makes DBSCAN really powerful when you don't know how many clusters you're looking for, when your clusters are oddly shaped, or when you want to automatically detect outliers. In this video, we'll walk through the algorithm step by step and apply it to the mall customers dataset to see how it performs in practice. Before we jump into the code, let's quickly go over how DBSCAN works. The goal of DBSCAN is to find clusters as regions of high density, while labeling sparse points as noise. It only needs two main inputs: EPS, or epsilon, which is the neighborhood radius, basically how far we look around each point, and minimum samples, which is the minimum number of neighbors required inside that radius to count as a dense region. With those two settings, DBSCAN classifies points into three categories. Core points have at least min samples neighbors inside epsilon and can form the center of a cluster. Border points don't have enough neighbors on their own, but they're close enough to a core point to join its cluster. Border points don't have enough neighbors on their own, but they're close enough to a core point to join its cluster. And noise points are neither. They don't belong anywhere and get labeled as outliers with a label of -1. The rules are pretty simple. Pick a point, check if it's dense enough to be a core, and if it is, grow a cluster around it by adding its neighbors. If a point doesn't have enough neighbors, it stays noise. The output is a label for every point, either part of a cluster or noise. The best part is that DBSCAN doesn't require you to set the numbers of clusters up front, so it's great for finding irregularly shaped groups and spotting outliers, though it can be a bit sensitive to the epsilon and min sample settings, especially when the dataset has clusters with very different densities. Let's start by importing the libraries we'll need. First, we bring in NumPy, Pandas, and Matplotlib, which are standard tools for handling data and creating plots in Python. Then, we'll import from scikit-learn, which is Python's core machine learning library. We'll also use standard scaler to scale our features, nearest neighbors to help us build the k-distance plot, and of course DBSCAN itself for clustering. Finally, we'll use image.io and IPython display image to generate and display GIFs later on, so we can actually watch how DBSCAN changes as we tune its parameters. Let's run our code. Let's start by loading our dataset. I'll be using the mall customers dataset from the Kaggle data science platform, which is a popular example for clustering. Let's run our code. Each row here represents a customer, and we have columns like customer ID, which is just an identifier for each customer, the customer's gender, male or female, age, which is the customer's age, annual income, their income in thousands of dollars, and spending score, some arbitrary score assigned by the mall based on their spending behavior and purchasing patterns. For our clustering, we're mainly going to focus on annual income and spending score, because these two features give us a clear picture of customer segments. The other columns are useful for context, but not directly needed for DBSCAN. Next, I'm applying something called a standard scaler. This makes sure both features are on the same scale. For example, income can be in the tens of thousands, while spending score is just 1 to 100. If we didn't scale, the algorithm would think income is way more important just because the numbers are bigger. By standardizing, we give both features equal weight in the clustering. As mentioned before, DBSCAN has two main parameters, that being epsilon and minimum samples. We'll set minimum samples to 5, which means a point needs at least 5 neighbors around it to count as a core point. A good rule of thumb is to start with a value between 5 and 8 for minimum samples, especially when you're working with simple 2-dimensional data like this. That range usually gives DBSCAN enough flexibility to form meaningful clusters without being too strict. Later, as we experiment, you'll see how increasing or decreasing minimum samples changes the amount of clusters and how many points get labeled as noise. Next, we need to figure out a good value for epsilon, which is the neighborhood radius. To do that, we'll use something called a k-distance plot. For every point in the dataset, we'll look at the distance to its fifth closest neighbor. Then, we sort all those distances and plot them. On this curve, you'll notice it gradually increases and then suddenly starts to rise more sharply. That bend, or elbow, is a good starting point for choosing epsilon. Below that value, points have enough neighbors to form clusters. And above it, points are further apart and more likely to be treated as noise. On this graph, it seems that around 0.5 epsilon value is where that elbow happens. While this isn't a perfect method, it does give us a reasonable place to start when tuning DBSCAN. Now, let's actually run DBSCAN. I've set epsilon to 0.5 and minimum samples to 5, which were the values we picked from the k-distance plot as a good starting point. When we fit DBSCAN on our scaled data, it gives back a cluster label for every point. Each number represents a cluster, and -1 means the point is considered noise, or an outlier. Let's run our code. As we can see, DBSCAN with epsilon at 0.5 and minimum samples at 5 only gave us 2 clusters and a handful of noise points. That's not particularly useful. It basically lumped most of our customers into one big group and only split off a small cluster at the top. This shows an important part of working with DBSCAN. The result depends very heavily on the parameters we choose. The elbow method gave us a good starting point for epsilon, but it doesn't always give us a perfect answer. So in the next step, we'll fine-tune epsilon by testing a few values around this range. By comparing how the number of clusters and noise points change, we can look for a better balance, more meaningful clusters without overwhelming amounts of noise. Here, I ran a DBSCAN across a range of epsilon values to see how the results change. With very small epsilon values like 0.1 or 0.3, DBSCAN is a bit too strict. It sees almost everything as noise and only forms a few tiny clusters. At the other end of the spectrum, like 0.6 or 0.8, it becomes too lenient. The clusters start to merge together, and eventually we just get one giant cluster with very little structure. Looking at the middle ground, around epsilon equal to 0.35, we get a much better balance. Several distinct clusters appear and the noise points are more reasonable. This is a perfect example of why tuning epsilon matters so much in DBSCAN. Too low and you end up fragmenting the data, too high and you oversimplify it. The sweet spot in this case is around 0.35. Let's take a look at how the other DBSCAN parameter, minimum samples, affects clustering. Remember, this sets the minimum number of neighbors a point needs to count as a core point and start a cluster. I fixed epsilon at 0.35, which is the value that gave us a good balance earlier, and varied minimum samples from 3 up to 15. With lower values like 3 or 4, DBSCAN is more permissive. It forms clusters more easily, even in less dense areas. That means we see more clusters, but sometimes they're fragile and not very meaningful. As we increase minimum samples, DBSCAN demands stronger density to form clusters. Some of the smaller groups disappear and more points get labeled as noise. With higher values like 12 or 15, DBSCAN is really strict. We end up with fewer clusters and a lot more points treated as noise. After experimenting with different values of epsilon and minimum samples, The configuration of epsilon equal to 0.35 and minimum samples equal to 3 works very well for the mall customers dataset. With minimum samples set to 3, DBSCAN can capture the natural groupings we can expect in this kind of data. At the same time, it still flags a handful of outliers, customers with unusual spending patterns compared to their income. Here, we get 7 clear clusters of customers, each representing a different income and spending profile. For example, we can see clusters of low-income, low-spending shoppers, clusters of high-income, high-spending shoppers, and everything in between. DBSCAN also identified 11 customers as noise, meaning that they don't fit neatly into any one group. That's useful too. These are our outliers, and in a business context, they might represent unusual or unique shopping behavior. This is exactly the kind of result we want from our DBSCAN model: meaningful clusters that match different customer types, plus the ability to detect outliers that k-means would have forced into a cluster. And that's it. We just built our first clustering model with DBSCAN. Unlike k-means, DBSCAN doesn't need you to pick the number of clusters ahead of time. Instead, it looks for dense regions of points and marks anything that doesn't fit as noise. We saw how important the two parameters are: epsilon, which controls how far we look for neighbors, and minimum samples, which sets how many neighbors are needed to start a cluster. By tuning those, we found a configuration that gives us clear customer groups and also highlights outliers. The big takeaway is that DBSCAN is great when clusters have irregular shapes or when you want to automatically detect unusual points in your data. It can be a little sensitive to parameter choices, but once you dial it in, it's a really powerful tool to have in your data science toolkit. If you found this helpful, don't forget to like the video, share it with someone else learning machine learning, and subscribe so you don't miss the next episode in this unsupervised learning series.